Welcome back to the Foundry by Forge College. I'm super excited to guide you through today's explainer. We are basically sketching out the exact blueprint for how Solana components communicate. If you remember, we're building directly on our previous lesson, the one about evaluating performance and scalability. There, we looked at how trade-offs affect throughput. But today we really need to understand the interaction patterns that actually make those performance goals operational.
So think about it like this. If you imagine thousands of high-speed components trying to process data simultaneously, but without a strict plan, it's literally pure chaos. It's kind of like 1,000 people trying to shout their coffee orders at a single barista at the exact same time. Total nightmare, right? So the ultimate question we need to answer is, how on earth do we coordinate them without slowing everything down to an absolute crawl? Let's dive into it.
All right, looking at our roadmap for today, we're covering chaos to coordination, orchestras and air traffic control, core patterns, a transaction's journey, the 5-step workflow, and finally, our key takeaways.
Section 1, From Chaos to Coordination, Meticulous Cross-Component Coordination. Now, we already know Solana is incredibly fast, right? Thanks to mechanisms like Gulfstream, which aggressively pushes transactions toward leaders early, and Sea-Level, which lets massive batches of transactions execute in parallel. But as the saying goes, speed without coordination is really just a fast collision. Without highly reliable interaction rules between validators and leaders, processing all those transactions in parallel would just result in everyone stepping on each other's toes. You don't get speed, you just get a massive system crash.
Moving right along to Section 2, Orchestras and Air Traffic.
To really wrap our heads around these abstract rules, let's use two completely different but complementary mental models. First up, the orchestra. An orchestra ensures synchronized execution, right? A conductor provides timing cues. They make sure everyone is playing from the exact same musical score, so the tuba player doesn't just go rogue and start playing a completely different song. On the flip side, we have air traffic control, or ATC. ATC provides well-defined message semantics, intent versus confirmation, so that two massive planes don't end up fighting over the exact same runway.
And we can actually map these metaphors directly onto our protocol roles. The leader acts as the conductor giving the cue or the ATC issuing clearances. They hold the primary responsibility for ordering transactions. Then you have the propagator or forwarder, acting as our relay station, aggressively and quickly distributing messages to tons of peers. Next is the executor or runtime, which is our pilot or instrument ensemble, actually applying the transactions deterministically. And finally, the state observer. This is our audience or our monitoring service, providing external visibility without actually changing the state itself. It's a super clean way to map exactly who holds ordering, propagation, and fault handling responsibilities across the entire system.
All right, Section 3, 3 core interaction patterns.
Let's define the 3 distinct interaction approaches that actually make all this work. First up, we have forwarding and propagation. This acts exactly like our ATC relay station. It's a many-to-many broadcast that aggressively pushes transactions toward leader candidates early on. And it uses what we call an idempotent relay. Basically, that means each node is smart enough to just ignore duplicate forwards. I mean, you definitely don't want your system bogging down processing the exact same forwarded transaction 50 times, right? Second, we have leader-driven coordination. Now, this is crucial because this is where our conductor steps in. The designated authority establishes a deterministic sequence for a batch of transactions. Basically, the leader asserts an order and says, hey, this is the proposed block, ensuring everyone across the network is playing from the exact same sheet music. And third, we have executor local synchronization. This is what allows our pilots, the runtime instances following that Sea-Level model, to run transactions in parallel. They use these really lightweight, deterministic scheduling checks to prevent non-conflicting accounts from crashing into one another. If 2 transactions happen to touch the same account, the executor uses the leader's exact order as a strict synchronization boundary to prevent conflicts. It's honestly brilliant. Which brings us to Section 4, a transaction's journey. Let's trace a single signed transaction as it flies through these patterns in real time. Just imagine you submit a transaction. First, you send it to a nearby validator who immediately forwards it. Second, it's blasted out via a propagation wave to multiple leader candidates and the gossip network. Third, a leader receives these forwards, runs their algorithm, and deterministically orders them. And finally, step 4, the executors receive the batch, divide them into parallel groups, and actually execute them. Forward, propagate, order,
execute, all happening in mere fractions of a single second. It's just an incredible high-speed dance of orchestrated components.
Let's get practical with Section 5, the 5-step design workflow. For those of you designing your own interaction surfaces, let's translate all this theory into a highly actionable manual. Step by step, you absolutely must explicitly design these contracts. Step 1. Identify responsibilities. You have to isolate exactly who reads, writes, or routes state. Step 2. Select your relay method. Do you need low latency, many-to-many propagation, or direct forwarding to a coordinator? Step 3. Choose your ordering authority. Decide if the leader's scope is global or partitioned. Step 4. Design minimal synchronization boundaries so you don't accidentally lock up the whole system for one tiny conflict. And Step 5. Specify fallback behaviors. Like if a forwarder loses connectivity, how do peers discover an alternative path? And this all builds into our core philosophy. Composable interactions prevent divergent realities. Following this 5-step workflow ensures you don't accidentally build an architecture that, looks brilliant on a whiteboard, but completely falls apart, stalls, or splits state when it's hit with heavy concurrent network load. If you don't define who the conductor is and exactly what happens if that conductor drops their baton, you are going to have divergent realities, period. Finally, Section 6, takeaways and next steps. If you take away anything from today's explainer, please make it these 3 foundational rules. First, always explicitly and strictly divide your forwarding, ordering, and executing roles. Second, purposefully match your interaction pattern to your desired outcome. So, use propagation for wide low-latency dissemination and leader coordination for strict ordering. And third, maintain minimal synchronization boundaries. Do not overlock your system. Keep those boundaries tight to keep your throughput soaring. I'm going to leave you with this final provocative thought. If a leader fails mid-sequence, who takes the baton next without losing the beat? Really ponder that fallback scenario, because it acts as the perfect bridge to our next module on synchronization mechanics and patterns. Thank you so much for joining me on this explainer. Be sure to visit Forge.college to learn more about this subject and explore our extensive library of other Web3 topics. Until next time, keep building and keep learning.